Hello, welcome back. So in the previous part, we have solved a problem. We have solved a problem to solve the reactions, to find the reactions actually. Now this is the second example in which we have to find out reactions of the beam because of these two UDL. There are two UDL this time. So first we will make a free body diagram. This will be the reaction. This will be the horizontal reaction, which is RH. This is RL. And the second reaction would be RR. And up to this point, there is one UDL, which is 4 kilonewton per meter. And the second UDL is of 8 kilonewton per meter. So in this case, we have to find out the reaction. So this distance is 1.5 meter and this reaction is 1.5 meter. So this time again we will assume the beam in the equilibrium. Assuming the beam in equilibrium. And then we will apply the equation of equilibrium. So as per equation of equilibrium, first equation is our Fx is equals to 0, which means summation of all the horizontal forces should be 0. So as you can see here in this beam, there is no horizontal force. So we will say that the reaction RH will be 0 because there is no horizontal force. Then we will use the second equation of equilibrium, which is Fy. So this second equation of equilibrium, according to this, all the vertical forces, I mean summation of algebraic sum of all the vertical forces should be equals to 0. So now what are the vertical forces that we have? So first is the reaction RL, then we have the UDL 4 kilonewton per meter, which is downward. Then we have the second URL, which UDL actually, which is 8 kilonewton per meter downward. And then we have the reaction RR, which is upward. So RL and RR will be upward force, so they will be RL plus RR. Similarly, the UDL, because of the 4 kilonewton per meter, it is spreading on 1.5 meter length. So the total UDL would be 1.5 multiplied by 1.5 multiplied by 4. So this is downward. So we will take this as negative. Similarly, the second UDL is again downward. So we will be taking this as negative 8 into 1.5. So there is only 4 vertical forces. So equating them equals to 0. So we can write this as RL plus RR is equals to 6, and this is actually equals to 18 kilonewton. So we will take this as equation 1. And now we will use the third equation of equilibrium, which is summation of m equals to 0. So in that case, we will say taking moment about, so last time we have taken moment, in the previous example we have taken moment about the A. Now this time I will be taking moment about B, because as the system, as the whole beam is in the equilibrium, so whichever point I take moment, the algebraic sum of all the forces moment of all the forces about that point will be 0. So this time I will be taking moment about B. So now this time I will think that, I will assume that all the forces are rotating about point B. So what are the forces? One is this one, this reaction RR, refer to this. Similarly, there is a reaction, this one, which is RL. Okay. And this is the UDL, this UDL, they are also rotating. So now, first, we will consider the effect of RL. So the rotation of RL reaction about point B would be RL into 3. So this RL will be rotating like this. So RL into 3. Similarly, the moment because of this UDL. So this UDL is 4 kilonewton per meter, and this is downward, and this will be rotating about B like this. So this is the anti-clockwise. This becomes the anti-clockwise rotation, and as this is the UDL spreading on 1.5 meter, so the total UDL will be concentrating on the half of this length, which is 1.5 meter. So this UDL, I'm just clearing the space. So now this UDL, first 4 kilonewton per meter. So the total UDL will be concentrating at the center of the length, which is 1.5 by 2. Okay, so the distance of this UDL from point B would be negative, because the rotation is anti-clockwise like this. So minus 4 into 1.5, that is the total magnitude of the UDL force, multiplied by the perpendicular distance. So perpendicular distance from B will be 1.5 plus half of this 1.5. So I will write here as 1.5 plus 1.5 divided by 2. Then we have the second UDL, which is 8 kilonewton per meter, and this is again will be acting at the center of the length on which it is spreading, which is 1.5 by 2. So the distance of this UDL concentration from the point B, it would be 1.5 by 2. So again it is anti-clockwise because it is rotating like this about point B. So this will become 8 into 1.5, that is the total UDL, and multiplied by the distance, perpendicular distance. So perpendicular distance will be 1.5 by 2. 1.5 by 2. Now this is the total moment. So we will now equate with the 0, because the moment because of this reaction force, which is RR, will be 0 about point P. So now after solving this equation, we can find out RL as 7.5 kilonewton. 7.5 kilonewton. Now using the equation 1, as you can see in the equation 1, RL plus RR is equals to 18 kilonewton. So we will use the equation, I will write here using equation 1. So we can write as RL plus RR is equals to 18 kilonewton. So putting the value of RL here, we can find out RR as 18 minus 7.5, which is 10.5 kilonewton. So that is the reaction. So now we can say that RL is 7.5, RR is 10.5, and RH is again 0 because there is no horizontal load. So that is the solution of this problem. So we will continue our discussion in the next part. Thank you.